Hello, good afternoon, and thanks for joining us today. My name is Amanda Sturkenberg, and I'm the European Marketing Manager here at REGENESIS. Now, before we get started, I have just a couple of admin items to cover. First of all, if you experience any issues with your audio or visual connection, then please log out, close your internet connection, and log back in using the link provided in your confirmation email. This usually solves the issue for most of the people. But if it doesn't, we are recording this webinar, and the link to the recording will be emailed to everyone once it is available, so you can always fall back on that. If you have a question during or after the main presentation, we encourage you to ask it using the webinar interface panel. Now, with this particular setup, you'll probably get an automated response, but I will collect all the questions and we'll do our best to address them at the end of the main presentation in a separate Q&A session. So today's webinar focuses on 6 pilot scale studies evaluating the in-situ treatment of PFAS in groundwater. We are very pleased to welcome our main presenter, Rick McGregor, President of in-situ Remediation Services Ltd in Canada. Rick has over 28 years' experience in groundwater and soil assessment and remediation. He's worked in more than 30 countries and has authored numerous papers on groundwater assessment and remediation. He holds an MSc degree from the University of Waterloo in hydrogeology and geochemistry and is a certified groundwater professional in Canada and the United States. Joining him today is Maureen Dooley, Director of Strategic Projects at REGENESIS. Maureen has more than 27 years of experience in the industry, and in her current role she provides technical leadership for complex soil and groundwater remediation projects within REGENESIS, as well as remediation design and strategy in the northeastern parts of the United States and eastern Canada. I will now hand over to Maureen to get us started.
Well, thank you and welcome everyone, and thank you for your time. The topic being covered in today's presentation is in-situ remediation of PFAS compounds. So our speaker, Rick McGregor, has been a pioneer in this subject area. So almost 3 years ago, he presented data from our first in-situ PFAS remediation site. And he's going to be presenting an update on that site, as well as some information on some new data from some new in-situ sites. But in thinking about this, 3 years later, what do we know about PFAS remediation and PFAS in general? I think, one, it's still really complicated. 2, our cleanup goals. While there's all kinds of variation between states and EPA, one thing we do know is that these goals are typically quite low. Also, we've had a number of sites been investigated, so more and more sites are being identified that have PFAS compounds. And so when we're looking at options for treatment, again, here we are 3 years later, what do we know? And honestly, we have two options really in front of us. We can use groundwater extraction with sorption, or we can look at in-situ remediation with sorption. So the only field demonstrated technologies that are available are related to sorption technologies. Other things are being evaluated, but that's what is available currently. So in Rick's talk, he's going to be presenting data from in-situ application of colloidal activated carbon. Now briefly, colloidal activated carbon, or plume stop, is a micron-sized particle that's suspended in a polymer, and that allows us to inject the material readily, easily, and under low pressure, and to allow us to get widespread distribution. And this is really important because this is a sorption-based remediation, and so our ability to get this widespread distribution is critical to achieve our remediation goals. When talking about activated carbon, quite often we think about granule activated carbon, or GAC, or PAC, and those are used quite often in what you're familiar with groundwater extraction systems. But when considering in-situ remediation, it's really important to look at the particle size. So something like GAC or PAC may be 50 to 250 microns, or 400 to even 1,000 microns. To be able to apply that in the subsurface is going to require high pressure injections, or fracturing. When using a liquid carbon suspension or plume stop, we have a particle size of 1 to 2 microns, and in this case we only need to have low pressure for injection. As an example, plume stop is typically applied using direct push, and if you click on the animation, you can get an idea of how it's injected and how critical it is to be able to get this distribution and cover the plume. If we're trying to achieve really low treatment objectives that are in the nanogram per liter targets, it's really critical that we get this distribution. Another point that comes up when considering remediation and using the in-situ application of a colloidal activated carbon is, how long is this remediation going to last? How long is this treatment good for? And one thing I think it's important to point out is that you have to look at this as a change in retardation factor. So when we apply plume stop or colloidal activated carbon, we're changing the retardation factor of the contaminants. So a retardation factor of a contaminant itself, if it's a number of 1, that means it travels with groundwater velocity or at the same rate as groundwater. If you have a retardation factor of 2, it's going to travel at half the speed. So the natural retardation factor for PFOA and PFOS is 3 and 19 respectively. But once you add the plume stop with the colloidal activated carbon, your retardation factor may go to 500 or 5,000. How that translates is, if you, for instance, have a site where you've applied a plume stop barrier at a mid-range dose, you can have a retardation factor at somewhere from 80 to even 4,000, depending on what the concentration of the contaminant is itself. And if you look at PFOS, your retardation factor may be as high as 10,000 for a concentration of 10 parts per billion, which is still on the high side for something that we may observe in a typical PFAS contaminated site. And again, how that translates to a remediation and how long your treatment may last, if we have a plume stop barrier with a dose that's, again, a mid-range dose of the plume stop, a width of 16 feet, an average seepage velocity and an influent concentration of 100 ppb, which again is on the higher side for many of the sites that we see with PFAS contamination, the transit time across that barrier may range from 57 years for PFOA or 200 years for PFOS. So what this translates to is you can have a remediation using plume stop that's going to last decades. So during the design process, we can harness the power of models, especially existing models, and that allows us to refine the optimal plume stop barrier placement. So REGENESIS has its own model, and we're able to incorporate the plume stop isotherm parameters into the model, and these are going to be individual isotherms for individual compounds. And then we're able to predict the longevity of the plume stop dose and ultimately optimize the dose that's needed to meet the desired longevity for the specific site. In this slide, we see a conceptual figure that identifies where you may be able to place an in-situ barrier using plume stop. You may have a site that is an airport or an industrial facility or a Department of Defense facility, and you may have concern about down gradient receptors. You're able to use plume stop to very immediately stop the migration of the PFAS compounds. In going back to how we started the presentation, I mentioned that 3 years ago, Rick had, presented on the first in-situ application of plume stop to address PFAS compounds. Here we are 4 years later, and we've completed 13 sites and have another 5 pending PFAS sites. So with that, I'll be happy to pass this on to Rick and start the presentation.
Oh, thank you, Maureen. So Maureen gave a brief overview of the PFAS, and as she mentioned, it's a very complicated topic. especially the fate transport and as well as the remediation. Today, I'm just going to give you a brief overview of some of the studies we've been involved in over the last 3 or 4 years now. So I'll start with a very brief introduction to PFAS remediation, some of it Maureen's already talked about. Then we'll move on to what I call the accidental remediation site that Maureen referred to, that we have about 4 years of data now. And I'll explain why it's an accidental site. And then we'll move into this 6 pilot scale study site that we recently completed. And then we'll start talking about some of the ongoing studies that we have going on with some of our academic and industry partners. So the current approaches are is pretty simple. As Maureen mentioned, is they're usually done by far the biggest and most applied method is pump and treat, using absorptive base materials, your granulated activated carbon or ion exchange resin, or combined to both those are combined to treat the groundwater. The challenges with this is there is no end in sight with pump and treat, and we've known that for 3 or 4 decades now. You generate a concentrated waste with the carbon or exchange resin, which either has to be regenerated or disposed of, which creates its own issues. And generally speaking, the approach right now is point of use treatment instead of trying to do plume management. So those are hot topics right now in the industry. Things that were being looked at, and this is not an extensive list by far, but more of the promising ones is for the waste or groundwater concentrate being developed, can we use thermal or plasma techniques to destroy the PFAS compounds in those? The plasma option is looking very intriguing, but once again, it has its limitations, one being the energy and the cost of it. But those are some of the ongoing methods being evaluated right now. For the in-treatment, if we thought the ex-situ treatment options were limited, in-situ treatment seems to be very limited. Really, there's only been one demonstrated technology to treat in-situ, and that's the activated carbon option. And there's various reasons why this, and this applies for above ground treatment too, is one of the reasons is most of us have heard, is called the forever chemicals. And that's because the chemists who invented them did an excellent job in making these chemicals resistant to breakdown. And that's due to the carbon fluoride bond, which is a very strong bond. Our challenges, as Maureen mentioned, is we have to get down to very low levels, nanograms per liter. So that in itself brings lots of challenges from a treatment point of view, as well as other things like back and matrix diffusion, which have always hindered or impacted remediation for any compounds that we deal with. When we start talking nanograms per liter, this even becomes more of a problem. Right now, lab or pilot approaches, the various oxidants and combinations of oxidants have been tested. Biochar, which is an absorption media, has been looked at. Doing bio methods is starting to emerge, and there seems to be some encouraging work on those lines. Then there, of course, is the classic activated carbon and ion exchange, as well as some of the reductants like zero-valent iron. So we'll start with the accidental site. This site was published about 2 years ago, I think about now, a year and a half ago. And it was a site here in central Canada that we're involved in because we're treating the petroleum hydrocarbons in the groundwater that were residue after an excavation was done. The hydrocarbons were, I would say, moderate concentrations here, with BTEX being about 300, the gas range about 2,000, and the diesel range about 3,500 micrograms per liter. So we did our design and chosen our reagents based on that. So we had chosen using plume stop to take care of the residue at the site. When we got to the site, literally the day we were going to start injections, the environmental consultant on site had mentioned had a small fire training pit at the site in this building that actually you can use for fabric coating too. So I don't want to say alarm bells went off my head, but at the time I said, oh. And so I grabbed some groundwater samples just before we injected and submitted them to a lab. Back at this time, there's very limited commercial labs who could do the testing and very limited PFAS compounds that could be tested. So at this time, really, it was only PFOA and PFOS that were really being analyzed. But sure enough, we did the remediation, but the samples came back a couple weeks later, and sure enough, both of those compounds showed up in the groundwater. Not at nasty high concentrations, but at moderate concentrations, I guess, based on what we're finding now. So the geology of the site and what we call glacial fuel deposit. So it's a sand with silty sand mixed in, and there's some sand lenses within it, about half an inch thick. It's a shallow water table site with water table about 3 feet below surface, unconfined. Our hydraulic activities are moderate. Our gradient is fairly high, but so we ended up with a fairly high calculated velocity of just less than a meter per day, which is a fairly high velocity. So, and it's key to remember here that the design here was done for petroleum hydrocarbons and not PFAS. At the time when we did the injection, we didn't know PFAS was in the groundwater. So this design was done for the petroleum hydrocarbons. So we used a 7 to 8 foot grid, which comprised about 20 locations. At each location, we injected about 200 liters or 50 gallons of reagent solution. It was done at low pressure, generally less than 25 psi, with about 630 pounds of plume stock being applied over the whole area. The figure in your bottom right there just shows the blue, baby blue blob is basically the hydrocarbon plume, and the part with the purple pseudo rectangle around it is the PFAS plume itself. So they weren't quite in the same areas, but the PFAS plume overlapped the hydrocarbon plume. So first thing we want to do was to look at the distribution of the petroleum, plume stop within the aquifer. Maureen, as she suggested, and anybody who's did in-situ remediation knows that distribution of your reagents is key to any success or failure of a program. So, and the nice thing about activated carbon is we can actually analyze for it in the aquifer, so we can get some idea of the distributions. So we collected cores for what we want to call the radius of influence, i.e. it was our design. We used a 7 to 8 foot grid. Was that design adequate? We wanted to see the target zone, and by that I mean, did the reagent go into the zone that we wanted it to go into? And by that we had about a meter wide thick impacted zone. Any reagents that are injected above or below that is basically a waste of reagents. And then we want to see the overall coverage. Did we get nice uniform, quote unquote, uniform coverage over the whole site? So this is the results of the distribution of the activated carbon throughout the whole site. So we just randomly picked 5 sites and we took cores, continuous cores using a geoprobe, dual tube sampler. And what you see is the 5 graphs. Those are concentration of organic carbon, which is in essence the activated carbon, with depth plotted on the y-axis. As you can see in the 2 dashed lines on each of those graphs is our targeted zone. That's where we wanted the reagent to go. And the overall conclusion here is yes, we did see our plume stop go into where we wanted it to inject. We did have some samples from below the zone that did have activated carbon, but not many. We seen pretty good distribution. If you look at the concentrations too, we've seen a fairly uniform concentration throughout the site. We do, especially on the graphs on your right, we did see some near the bottom of the target injection zones, a couple peaks, and those are related to the sand lenses. So we did see some heterogeneity with the respective distribution due to that high conductivity sand lens that we talked about. So this slide just shows the results of the radius of influence, if you want to call it that. I prefer area of influence. Radius implies a nice uniform injection, which we all know doesn't exist. Once again, same idea. We plotted, we stepped out from the injection point, which is that square red dot, and we stepped out 2 feet, 5 feet, 10 feet, and 15 feet, and we wanted to see how far out we actually detected the plume stop from. And you can see here, even though the concentrations decrease with distance, we did get detection of the plume stop at a distance of 15 feet from the injection point. So this confirmed, at least at this location, that our 6 to 8 foot injection grid was valid, and that we should get uniform coverage. And once again, we see with here that most of our plume stock ended up in our target injection zone between 2.5 and 5.5 meters. So this is probably the most boring results slide you'll ever see, but it's a good slide. And that the 6 wells that were near or within the injection zone, this is the PFOS, PFOA. This is over 48 months of monitoring. So we just collected our 48 month samples back in the spring of this year. And we see for PFOS and PFOA that it was basically been non-detect since the injection of the carbon. So we haven't seen any rebound, we haven't seen any breakthrough. It's been non-detect since. We've had 1 or 2 hits of various PFOS compounds at the detection limit, but they immediately went back down to non-detect during the next sampling period. So we think that's maybe an analytical issue. After about a year, we did start analyzing for other PFOS compounds. And once again, we've never detected any PFOS compounds since then. So yeah, the results have been very encouraging, and we see right now at 4 years and counting that we still haven't seen any evidence of the plume stock being consumed or releasing any of PFOS compounds. So the preliminary observations, and I call them preliminary because this site we hopefully will continue monitoring for a fairly long time to see what the lifespan is of this of the injected plume stock that we did. But we've seen very good distribution. 96% of the plume stock we injected went into the targeted injection zone when we do our mass balance. We've seen a fairly uniform distribution within the target injection zone. And we've seen basically up to a 5 meter radius of influence. So very good and excellent distribution, which is always a challenge for in situ. The chemistry is the PFOS and PFOA were being non-detect for 4 years. The other PFOS compounds have all been non-detect. And really the reason we did the actual injection was for the BTEX and petroleum hydrocarbons, which have remained below regulatory limits for 4 years and counting. There's an excellent paper put out by Dr. Grant Carey, who took the results of the study and did some numerical modeling to look at lifespans, predicted lifespans and that. And I do have I think the next slide will show you his paper, but that gives very good, and it sort of confirms what Maureen was talking about earlier, is that we're looking at lifespans of the plume stock for decades based on what we know. We also did some biochemistry of the plume, both within and outside the PFOS plume, and we did see some various interesting results and various changes in the microbiological community. I won't get into those now, as I'll let you read the paper. And remember that this paper was published prior to the biological findings that are starting to pop up. So there might be something in there that is of interest. So here's just the 2 papers that have been published. They're both in the Remediation Journal, and you're welcome to look them up, and hopefully you don't fall asleep while you read them. But here they are. They're one's by myself and one's by Dr. Carey and some of the co-authors. So we'll get into why we're here today. So this is as a kind of a continuation of the study we just did. We're interested in, there's lots of tests going on, lots, especially laboratory tests, looking at various compounds. And so we wanted to look at some of these. And we had an opportunity at a site to do a bunch of pilot scale testing. So as you can see here, there's, the absorptives, which is the activated carbon, biochar, and ion exchange rates. We knew those would kind of work based on above ground treatment. Oxidants, there's been a fair bit of work done using oxidants, especially persulfate, some hydrogen peroxide. For the persulfate, both activated and unactivated, and I'll get into what we use later. Then there's been some work on reductants, and there's even some encouraging results done by the STAR technology out of Western University here in Canada, who's had some very promising results using, it's a smoldering technique. So what we want to do with these pilot scale tests was look at the evaluation over time of the treatment, distribution of reagents, the effect of heterogeneity on the reagents, lifespan of any of the reagents. And one of the things that was being brought up by our authors, Fox et al., was, do we see preferential accumulation in pre-existing sandpacks of wells, which could potentially bias any results we see? So we wanted to look at that. So once again, this is a large petroleum hydrocarbon facility. It had a large, very large BTEX plume, probably one of the largest I've found in the literature in the world. Once again, our BTEX was about 680 micrograms per liter. Our gas range was about 3,500, so nothing overwhelming. And this is in the area where we were doing the pilot scales. And once again, we analyzed for 22 PFAS compounds, and we found 6, and there you are. So we've seen a nice range of some very light short chain carbon right up to some 8 to 9 carbon chain compounds. So we've seen a bit of a mix. And the reason we find this at these facilities is the facilities required once or twice a year to do training for their fire department, and one of the things they use is firefighting foam as their testing. So they once or twice a year they apply firefighting foam in various areas of the site as training mechanism. So that's why we're looking for it at the site. So the geology is a fine sand. With it did have as there usually is, a higher conductivity lens within the sand. It turned out about 1 inch thick. So once again, it was an unconfined aquifer with a water table about 17 feet below surface. Our mean hydraulic conductivity, horizontal hydraulic conductivity, is about 10 to minus 5 meters per second, with a fairly high groundwater flow, about 200 feet per year. The geochemistry, since it was a petroleum hydrocarbon plume, was an iron sulfate reducing plume. So what we did was we installed or injected 6 permeable reactive barriers or zones, so basically side by side by side. And we injected a different reagent within each one. And those are the 6 reagents we did. We did a colloidal activated carbon, i.e. plume stop. We did a powdered activated carbon. We did a biochar, and we did an ion exchange, and we did a sodium persulfate and the hydrogen peroxide ones. The sodium persulfate was unactivated. And the reason we did that here is we're really concerned about mostly the BTEX from a risk point of view. Plus the groundwater at the site has a natural temperature ranging about 27 to 30 degrees Celsius. So it has a very high groundwater temperature, which actually self-activates the persulfate. We knew that unactivated persulfate worked best for the petroleum hydrocarbons at the site, based on work done previously by myself and Dr. Maureen, as well as the University of Wiley. There's some papers published on this, so we knew that would work well. So that's why we wanted to test activated persulfate. We used a fairly dense grid, a 5-meter direct push grid with geoprobe, and we injected over multiple intervals in the target zone. And on your right there is just kind of a general schematic of each pilot scale area. So you see the 8 injection points, plus where we took cores. The regular monitoring wells, we had 3, 1 up gradient, 1 within and 1 down gradient. Those are regular 2-inch. And we also installed a CMT within each well. And a CMT is a multi-leveled well sold by Solence in Canada here. It allows for very discrete vertical samples. They're about 6-inch screens, and you can put the screens anywhere you want. So we installed that just to get a better idea of flux zones and vertical distribution of the PFAS within the shell aquifer. So groundwater monitoring, we're looking at as I said, the combination 2-inch and CMT wells. The typical chemistry, nothing too exciting here. We just did the regular things. We did 5 sampling events plus 2 pre-injections, so a total of 7 sampling events, basically the 2 pre-injection, then 3 months, 6 months, 9 months, 1 year, and 18 months after injection. We took lots of cores of the aquifer and analyzed them for total organic carbon, which is not quite accurate as it incorporates the activated carbon part of things. We looked at the pore water for persulfate and hydrogen peroxide, and all the cores were taken by direct push. We also did aquifer testing, and specifically we looked at the hydraulic conductivity, horizontal hydraulic conductivity of the aquifer, both pre and post injection, for changes in, if we actually seen changes in the hydraulic conductivity. And the cores were taken back to the laboratory and used a flexible wall permeameter to test those. So each cell was about 40 square meters with 8 injection points. Direct push was used, and we injected all reagents at about a 10-weight% concentration. That generally will not happen. Everything's going to be customized depending on your thing, but we want to try to minimize variable. So we used a 10 weight percent. Now a lot of these compounds are very effective at 10 weight percent. Some is higher, as in hydrogen peroxide. 10 weight percent is a bit high for general hydrogen peroxide. It's maybe a bit low for persulfate, for plume stop, and activated carbon. Those are about right. Ion exchange, there really isn't much literature out there for injecting ion exchange resin or biochar. So the big change here was for the pressures needed, and we went in at the minimum pressures that we were allowed, and that was allowed for the injection of these reagents. So any of the coarser grain materials, the powdered activated carbon, biochar, and the ion exchange resin, we had to go into high pressures. Generally, they were about 220 to 250 psi just to get them in. So we were fracking the aquifer. There's no doubt about that. For the soluble and components, the hydrogen peroxide, persulfate, and activated colloidal activated carbon, we were generally less than 25, or sometimes we get up to 35 psi. So this is some slides of hydraulic activity, one core taken in each cell pre and post injection. What you'll notice here is you'll see in the pack and the ion exchange and the biochar, you'll see between the post and pre-injection, you'll see a big change within and that dashed line is the sand seam, the high hydraulic conductivity sand seam. You'll see a big change in the hydraulic conductivity, up to about 3 to 4 times higher post-injection. Post-injection, the hydraulic conductivity increased post-injection. And at first that seems counterintuitive because you think you're injecting a salt that should plug the aquifer, or may plug the aquifer. The reality is what we think is happening here is we actually, to inject this, we actually had to fracture to get this in the ground. So most of the reagent, and we'll see in later slides, for these 3 compounds went within this high conductivity zone and created a fracture to get it in, and therefore we're actually increasing the hydraulic conductivity of that sand seam. How that impacts the mass flux and other treatment properties of those reagents with time, well, we'll see those results later, but that's what we think was happening there, is we're seeing a fracturing of that sand seam, and we'll see what the effects of that later on. The other thing is the samples were collected about 24 hours after the injection was done. So they were collected very quickly. Actually, almost all the results here you'll see were collected with respect to cores 24 hours post-injection. So this just summarizes, but what you see is almost an order of magnitude change in some of the hydraulic conductivity change within the pack, biochar, and ion exchange after the injection. So we think that's once again due to hydraulic fracturing of the sand seam. So this is more of an interest for mass flux. So the people out there who really like mass flux and through aquifers, this was using CMTs, and all we did was install a 6-inch screen at 5.5 meters, one at just below 6 meters within the high conductivity zone, and one at about 7.2 meters. And we just want to see what kind of flux we're seeing. Do we see a vertical distribution of the PFAS with depth? And you'll see in all 3 or all 4 profiles here provided that we see a vertical distribution of the PFAS compounds, with the exception of the, and this is post-injection, with the exception of the colloidal activated carbon, which showed a more uniform distribution with depth. And we'll get into the reasons for that. This is after about 1 year treatment. So let's just summarize it. We've seen a breakthrough within the target zones of all the compounds except the colloidal activated carbon. We see the highest flux by almost order of magnitude within the high K zones. No surprise there. We've seen the low carbon chain length PFAS compounds break through before the higher number of carbon chain PFAS, which is not unexpected, especially for absorption-based media. So you have to sit back, and how this impacts our treatment systems and our monitoring. Are large screens not representative of the potential mass loading? I think there's been a long time argument out there that they don't. Small heterogeneities can have a massive effect on mass flux, and can this lead to premature failure. None of this is really any new. It's not new, but it's stuff that just confirms that we need to look at these things on a small scale sometimes, especially when contaminant remediation. So the next thing we want to do is look at what was the effect of the high K zone, the sand lens, on the distribution of the injected, whatever we're injecting. In this case, I'm just going to deal with the carbon-based compounds, so the colloidal activated, the persulfate activated, and the biochar. And we wanted to see is, did that high K zone affect the distribution when we injected, i.e. did everything, or I shouldn't say everything, but did the largest proportion of mass that we injected ended up in this high K zone? As you see from the graph on the left, the colloidal activated carbon, we actually seen a fairly nice distribution from about 5.5 down to 7 meters, which was the target injection zone. But when we contrast that with powdered activated carbon biochar, we see very, very unilateral peaks within that sand seam, suggesting that what we injected in both of those cells, most of it was injected within that sand seam and it was controlled by that sand seam. So the next question, of course, is how does that impact treatment, if any? So this just gives you some of the stats. I won't go into them. You can read them if you really like to. But we did a fairly detailed analysis of the concentrations of activated carbon, or total activated carbon, or total organic carbon inside and outside our targeted injection zone. And that first 2 lines is how much went into where we wanted to go into. So you see for the colloidal activated carbon, the concentration was 7 times higher within the target activated zone, which is very good, and that directly impacts that retardation factor that Maureen was talking about. Pre-injection, we did FLC analysis of the aquifer, and you can see we started at 0.006 grams per kilogram, and once we injected within the target activated zone, we increased to 0.77. So we increased it by 3 orders of magnitude, which, as you can imagine, for a retardation factor, that's at least 3 orders of magnitude greater retardation factor. So that was that's significant. Also, we've seen 100% of the samples we collected within that target zone had detectable activated carbon in it versus 1/3 of samples outside the target zone, which tells us that we're getting things where we want it. So for the powdered activated carbon, once again, we've seen within the target activated zone, we've seen a fairly similar number, 0.79 grams per kilogram versus the 0.77 for the colloidal. But what we're seeing is that's heavily influenced by the sand seam, which had 2.4 grams per kilogram within it. So basically, if you back out the average, you'll see that really outside the sand seam, the rest of the target zone had very nil activated carbon injected into it. And that's kind of shows as well. We still see fairly good high number of samples within the target zone having detectable activated carbon, 67%. Versus outside, but still we see a drop compared to the colloidal activated carbon. So biochar, which is even a coarser version and not as high as absorption capacity, we see similar results, and we see once again that sand seam contained the bulk of what we injected. And then we see it about the same type of numbers within and outside the target injection zone as we see it for the powdered. So, if you went on this, the colloidal was by far the best distribution, followed by the powdered, followed by the biochar. So the results. So we'll start with the colloidal activated. We'll start with the good and end up with not so good. So this is just, I picked 3 of the PFOS compounds, basically tried to vary the number of carbons. So the PFPeA and the PFBA is basically short chain organic carbon. PFAS, where the PFOA is generally a longer chain. So we want to see, does the number of chain carbons in the chain actually impact, and it should impact the treatment efficiency of any absorptive medium. So what we see here is you see on day 0, that was when the injection was done. You see the concentrations come in, and then basically the first monitoring event after on 3 months after injection, we see everything and go down to non-detect, and that's up to 18 months post-injection. So nothing I mean, that's great results, but nothing too exciting happening there. It's great results. So for the powder activated carbon, we see once again, you know, after 30 days, 90 days, we see very good treatment, all non-detect. But then we start to see breakthrough of the short chain activated PFAS compounds. And we don't see them all breakthrough at first. We see basically the shorter chain, the C4 or C5 breakthrough before we see the C8s. So that, you know, that's telling us that maybe we have preferential absorption happening, which is what we would expect. And maybe we're also seeing something to do with the mass flux through the high K zone. Is that flux in there is just too high for the amount of mass of powdered activated carbon we put in the ground. So, so that was interesting, and then we'll go on to the biochar next. And once again, we see something similar to powder activated carbon, with even probably faster breakthrough. It's hard to tell, but once again, at 90 days, everything was hunky-dory. And then at 9 months, we see breakthrough of all three compounds, and we almost see breakthrough back to the original inputs, except, which suggests that the biochar is basically exhausted from an absorption capacity point of view. So how does this impact was this just due to the limited absorption capacity of the biochar, or was we having so much mass being funneled through that high K zone that we're just overloading the biochar too quickly and too fast? So hydrogen peroxide. Now, I'm not going to joke with anybody. We expected no treatment from hydrogen peroxide. We just did it because we had other motives at the site as well as the PFAS. So in this case, what we seen was what we expected, zero treatment whatsoever. And actually we see some production of some of the lighter, it appears to be some actual production of some of the smaller carbon chain PFAS compounds, but we can't really say for sure, but we suspect that we might be seeing some production of that from precursors and such thing. So the sodium persulfate, remember, it was unactivated because we had the high temperature. We weren't quite sure what to expect for this. Persulfate has shown, I guess, mixed results with respect to PFAS. So we weren't quite sure what we were injecting. Now we were going in at a lower concentration and we weren't activated, but we do have heat activation, which is generally considered one of the more aggressive activation types for persulfate. So but what we see here is we did see some treatment of PFOA, so the longer chain carbon, but we see nothing for the shorter chain. So, and then once again, that was gone after 90 days. And then we're back to basically input concentrations. And I should mention that all these samples were collected at MW2, which is in the middle of the barrier for all this, for all the tests. Ion exchange resin was probably the most interesting of them all. We expected very good results. We don't know if ion exchange resin is practical. It's very expensive. But we were expecting very good results from this, and we did get very good results for the first 6 months. And then we started seeing this preferential breakthrough with the lighter chain coming through first, and then followed by the progressively more longer chain PFAS. But once again, since we think this premature breakthrough, and we're calling it premature breakthrough, is probably related to the distribution of the ion exchange within the aquifer, i.e. it's mostly gone into the sand seam, high conductivity sand seam, and as well as the subsequent mass loading due to the increased hydraulic conductivity of that seam after injection. So we think that's probably what's causing this. But right now we have nothing definitive to say that. But anyway, these were probably the most interesting results. So what we've seen was we had breakthrough for all the PFAS compounds within all the test cells, with the exception of the colloidal activated carbon. The hydrogen peroxide and persulfate, as was expected, really had complete breakthrough in 90 days or less. And we also did see preferential breakthrough of the low carbon chain PFAS compounds with respect to the longer, higher chain carbon chain PFAS compounds. I realized after I did this slide that I probably have this backward for some people, but in order, I put it in the order of breakthrough. So we had breakthrough first for PFAS compounds with hydrogen peroxide, and persulfate is about the same. Biochar was next in line, then the ion exchange, then the powdered, and finally the colloidal activated carbon, which we did not see any breakthrough. So this is kind of in order of how fast breakthrough will occur. If you want to spin it the other way, you would put activated colloidal activated carbon first, as in it's showing the best treatment at this site anyways. So these are just some bar graphs just showing the treatment of after 1 year of the I picked 3 of the PFAS compounds here, and just comparing them amongst their each of the things. So you can see with the colloidal activated carbon, we're always getting basically 100% treatment versus we're on for some of the peroxides and persulfate. We were not getting any treatment, and in some cases, we were actually producing some of the PFAS compounds, it appeared. But that said, and generally speaking, once again, you can see here that we got better treatment for longer carbon chain PFAS compared to the shorter chain PFAS. So this is one of the more interesting things. There was some work done by Fox et al. About potential sand packs being impacted, and these are pre-existing well. And the idea, the hypothesis was, when you're injecting something that's coarse or particle, could it accumulate in the well screen? Basically, the well screens are designed to remove particulate and fines. So could it be actually doing the same thing with respect to anything you inject? And the injectant would go into the well screen and be removed. But the problem with that would be are you actually creating a well screen that's full of your reagent that you injected, and which could potentially give you biased results? So based on that, we took took some thinking, but we went to pre-existing wells, and then we took very small cores using a geoprobe, going down the sand pack and collecting these cores beside the sand pack, and then analyzing them. And as you can see here, we analyzed a lot of samples, very fine detail, about 25 centimeter intervals, or just about 7-8 inch intervals. And we compared the results before and after injection. So in this case, I'm just giving you the red samples, the red dots, sorry, represent the concentration of activated carbon or total organic carbon within the aquifer beside the sand pack, versus the open squares, which are the concentration, TOC concentration, within the sand pack itself. So we want to see are we getting preferential accumulation within the sand pack? And you can see with colloidal activated carbon, no, it looks pretty good. There is some jumping around there, but if you actually do the mean and standard deviation, the sand pack has less activated carbon in it than the surrounding aquifer. Unlike the powdered and biochars, which actually show a very big increase in the sand pack compared to the surrounding aquifer where it was injected. The one interesting thing here too is we see the activated carbon in the biochar and the powdered activated carbon, we see it looks like it's entering the sand pack through the high K zone and then kind of distributing itself vertically within the sand pack. The results are looking that way. But anyway, at the end of the day, there was no doubt that we're seeing preferential accumulation of the activated carbon or biochar, powdered activated or biochar within the sand pack of pre-existing wells. So this just provides the statistics. You can look at it later, but but you can see there is a significant increase in the sand pack, the accumulation of the reagents within the sand pack for the powdered biochar, where from the colloidal, we don't see, if anything, we see actually a decrease. And this has all been published in a paper that came out a couple months ago. So once again, it was in the Remediation Journal, so you're more welcome to download it. So just a brief couple slides on ongoing studies we're involved in. One was we decided to make our life really difficult, so we picked a fractured bedrock site in central Canada here in Ontario, where there was a fire at a residence that had a nail shop attached to it, and the fire department decided to use foam to extinguish the fire. So they really were stuck with what to do. So they had read these papers actually and asked us if we would try the colloidal activated carbon, the plume stop injection. So we did. That was done earlier this year. I'll present some of the results we just got back. So it's very early in the study. We're doing more work in saline aquifer in Middle East, bulk thing, where we're looking at PFOS in once again a hydrocarbon plume, and after 18 months we have non-detect for all the PFOS that we're detecting. And then of course the accidental site, which I showed originally, we're at 5 years. We're into the 5th year now, so we plan to continue analyzing that. So this is this fractured rock site, and these results literally came to us last week. So they collected a lot of data before the injection happened, and so they have up to almost 2 years of data beforehand. And you can see some of the concentrations are rising. I just picked 3 wells within the rock itself. Concentrations are not high, but up to 1,000. And this is total PFOS. So our ministry up here has asked for the remedial value. They haven't really established one, but at this site they said they want the total PFOS compound to be no greater than 70 nanograms per liter. So that's kind of our target. So these are the 3 wells. You can see that we see 2 of the 3 wells, we see dramatic decreases in PFOS, and basically down to detection limits. So in this case, we're down to about 4 nanograms per liter for the detection limit. So excellent thing. At the 3rd well, MW4, we do see a decrease, but not as dramatic. And right now we're trying to understand what's going on there. And so I right now don't have an answer for that. So I know the environmental consultant is going out in a couple more weeks to do some more sampling. So we'll see where the results are there. But overall here, fractured rock concerns, fractured rock. We're pretty happy with the results, and we'll see where we'll go from here. So we're also involved in a academic industrial group up here in Canada that's doing a lot of good work, some funding through the Canadian government as well as industry funding. And there's 3 groups in University of Waterloo, University of Toronto, as well as Carleton University in Ottawa, Ontario. They're doing various laboratory stuff, trying to understand more of the fundamentals here. And they include isotherm studies, look at absorption, look at cold competition studies with different chlorinated solvents or petroleum hydrocarbons, look at that competition between absorption. There's basic analytical issues with these things. That is still very much evolving science, as anybody who's tried to analyze PFAS. And then we're planning to step up to some column tests, look at some 1 and 2D flow. And then meanwhile, there'll be some numerical modeling, partly done by Dr. Grant Carey, as well as Dr. Brent Sleep and his students, and Dr. Paul Van Giel at Carleton. We'll look at some, and their students will be doing some numerical modeling. And then we have proposed, and we're partially hopeful that we can do a field test at the CFB board, in which anybody who's in hydrogeology probably recognize that name, where University of Waterloo and amongst other researchers have spilled over the years a multitude of contaminants, and we're hoping to add to that this PFAS. So we're hoping to hear shortly about our funding request for that. And so I guess I'll wrap it up. I'd just like to thank once again our academic partners and University of Toronto, Carleton, and University of Waterloo, as well as right now we have a couple of industry partners, ourselves and Port Water Solutions. We're always looking for more people to join. So anyway, if anybody's interested, they can give me or Dr. Grant Carey an email, and we'd be more than happy to talk. But for now, I think that sums it up, and I guess we'll take some questions.
Okay, thank you very much, Rick. Now, before we move into the question and answer session, just a couple of reminders. After the webinar, you will receive a follow-up email with a short survey. We really appreciate your feedback, and it will help us keep the events hopefully relevant and of interest to you. So please take a minute to let us know how we did. In the survey, there's also a space to request certificates of attendance, which may contribute to your continual professional development, CPD. So if you'd like that, please don't email me directly, but fill in the questionnaire, as it makes processing these certificates a lot easier. Also, after the webinar, as I said before, you will receive a link to the webinar recording as soon as we can make that available. Now then, let's have a look at the questions. Okay, so here's the first question. Would we be expecting similar results with other compounds, such as chlorinated solvents? Maureen, maybe this is one for you?
If, presuming that the question is related to some of the breakthrough that was observed with some of the, the char or the PAC-GAC that was evaluated in the pilot test, I think we could assume the same kind of results might happen too with chlorinated solvents if you have increased flow, or if you have some of the compounds where the isotherm is a little less favorable, say, DCE versus PCE, you might see something similar. Something that really wasn't, brought up earlier. We talk a lot about injection and distribution, but one of the other attributes to the plume stopper colloidal activated carbon is that there's a lot of surface area because of the 1 to 2 micron size of the particle. So what that allows for is really better kinetics for sorption. So you're going to have faster sorption, and you have all of the surface area. So ultimately you have greater efficiency.
Okay, thanks, Maureen. Right, so there's a lot of questions about your study here, Rick. Here is the first one. How did you measure the activated carbon in soil?
Yeah, that's a basic question, which was actually very hard to do. We ended up using a combustion method that was based on using a legal furnace that basically gives us a total carbon result. From that, we had to back out the basically the carbonate portion of that. So the results we present, I've simplified them, but they're basically a corrected number. But to answer your question is that we use basically a combustion method to do the analysis.
Great, thanks, Rick. The next question is, what about the BTEX in the pilot scale test area? How is that being addressed?
So overall, the BTEX set, this is a large plume, so it's being addressed by a variety of different technologies, including air sparge, SV. These are in different areas of where the pilot tests were done. There's been some other plume stop applications in some areas. There's been some chemical oxidation done in some areas. So this test was done, and some of those results of those tests have been actually published previously, and anybody's interested, I can forward those papers. In this case, these pilot scale tests were kind of done to look at BTEX, but more specifically look at the PFOS in specifically is where these tests were done for the PFOS. The other BTEX was being done by other things. So what we envision overall is ideally we can get one technology that can treat everything. The reality is we're probably looking at some sort of sequential treatment or some sort of hybrid treatment where we're using different technologies, just different things, because we also have MTBE and TBA in this plume, which is, as anybody knows, can be problematic from a treatment point of view too.
Okay, thanks. Here is another one. How did you sample to measure the TOC in the sand pack?
So we sort of talked about it, and I glossed over it pretty quick, but we basically used a very small sampling tube, which is about 3/4 of an inch in diameter. And we basically went down, not quite beside the well, but between the well and the annulus, within the annulus of the borehole, and direct pushed and collect the samples that way. So we used a modified method it's called the Starr-Ningleton method. It was published back when I was a grad student, so that was a long time ago, probably in the early 90s, late 80s. So it's basically, it's kind of a direct push method, but it's that's you get in more tighter spaces.
Okay, thank you. And here is the next question. How long after the injection did you collect data to measure groundwater flow? And how did you measure the change?
So we collected the cores for hydraulic conductivity approximately 24 hours after the injection was done. Those cores were collected using a geoprobe, dual tube sampler method, and then those samples were basically subdivided and frozen, and then we were taking them back to a laboratory where we did the flexible wall permeanders on. There had to be some methodology changes there just because of the flexible wall permeanders deal with a certain size, so we had to do some modifications there, but that's basically how they were done.
Okay, thanks, Rick. Now, there's kind of two questions that I'm going to ask in one. How do you most effectively inject or install plume stop? And the other one is, how do you confirm adequate distribution in the high flux regions?
So we generally speaking, in overburden deposits, we always prefer to use direct push. There are a variety of different direct push methods out there. There's approaches, there's tops down, bottoms up. In this case, we use the bottoms up method, but we used a very specialized screen that allows us to do very discrete intervals. So there are screen tools out there that can close and open on depths you want. So there are a variety of options out there to do that, but we use the bottoms up method with a small screen, injection screen. The way we confirm within the high K zone is very discrete coring using the continuous core, the dual tube, where we sample, we knew exactly where that zone was and we sampled over it, and we would actually subdivide that when we collect the core, take that sample right out and separate it from the rest of the above and below aquifer samples.
Okay, great. Thank you very much, Rick. We've just come to the hour, I see now, so I think we'll have to end the Q&A here. If we didn't get to answer your question, don't worry, somebody will make an effort to follow up with you within the next couple of days. For more information about remediation services from Rick's company, InSitu Remediation Services Ltd, you can visit irsl.ca. If you'd like to learn more about remediation solutions from REGENESIS, then please visit our website regenesis.com/EUR. Thanks again to our presenters, Rick and Maureen, and thanks to all of you for joining us. Enjoy the rest of your day. Goodbye.